Okay, cyclic groups. 10. So problem here, let A be an element of order 12 in a group G. Find the smallest positive integer r such that 12 divides 10r. So just you say 12 divides 10r, that means 6 divides 5r. 6 cannot divide 5, which is logic we'll use quite a bit here. So this type of logic. So that those facts mean that 6 divides r mean, so r equals 6. And a lot of these are pretty quick. There's only one really, out of the 3 big things, only one of them's long. Find the smallest integer s such that a raised to 10 raised to s equals e. So a to the 10 s is what this means, equals e. Order of a is 12, that means 12 divides 10s, which means it's 6 divides 5s, which 6 divides s, so s equals 6. What is the order of A10? Order of A10 is 6 as seen in part 2. Order of A10 equals s, where s is the smallest integer s such that a to the 10 to the s power equals e. It's basically y. And that's the order of power of it. And what is the order of a to the 7th now? Order of a to the 7th equals smallest r is in z, positive z, such that, positive integers I mean, such that a to the 7 to the r power equals e. A to 7r equals e implies that 12 divides 7r, which means that 12 divides r, because 12 and 7 are relatively prime to each other, so that won't work. So 12 has to divide r, and that means r equals 12. So order of a to the 7th equals 12. And let's make our lives easier. Let's do this one. Then I'll explain the really long one. I'm going to skip backwards after this. 22. Let G equals A. That's like to be a cyclic group of order 18 in that design. The brackets are. List all the elements of order 2 in G. We know A to the 18 equals E since order 18. Find K for A to the K such that AK to the second power equals E. A to the 2K equals E implies that 18 divides 2K, which means 9 divides K. And GCD of K 18 equals 19. So that means that K equals 9. Yeah, you just really pay attention at GCD though. K equals 9 is the only one, so that means because K can be anywhere from 0 to 17 integers. So this means that A to the 9 has order 2 in G. List all elements of order 3 in G. A to the K is in G such that AK 3 cubed equals E implies that A to the 3K equals E. That means 18 divides 3K, which means 6 divides K, so GCD of K 18 equals 6. So K is in 6 and 12. It's the only ones that all work. It's A to the 6 and A, so A to the 6, A to the 12 have order 2 in G. K can only be within 0 to 17 range. So if order 2 in G is A to the 6 and A to the 12. List all the elements of order 6 in G. A to the K is in G such that, again, that's saying you get A to the 6K equals E, so that means 18 divides 6K, which means that 3 divides K. GCD of K 18 equals 3. K can be 3 or 15. So A to the third power A to the 15th is order 6 in G. If you want, you can test every single number that you can think of, but those are the only ones that work. You can do it in you can write them out real quickly, GCD of every number. And finally, D butters to list all the generators of G. This means so there's a question, list all the generators of G. This means all elements of order 18 in G, A to the K is in G such that AK to the 18 power equals E, which means A to the 18K equals E. 18K Oh, 18 divides 8 to k, which means that 1 divides k, so GCD of k 18 equals 1. And that means k is in 1, 5, 7, 11, 13, 17. So a fifth, a 7th power, a to the 11th, a to the 13th power, and a to the 17th power are generators of G. You can try this out. One thing that's obvious though, it's not an even number though, because 18 is even, so any even number won't work. And anything that has, multiple is 3 as well, because obvious. 18 and anything with 3 will have divided by 3. One way to think of it. So you're very limited. But that's how that works. So that's 2 palms down now. Now it's time for the long one. Let V be the multiplicative group of the non-zero complex numbers, and let alpha equals 1 plus I divided by square root of 2. So list the elements of the cyclic group, the cyclic subgroup alpha and V. Okay, I wrote all down here and I show my work, but you can do this by converting this to polar coordinates, which I'll show in a little bit. But first, let's just do this another way, just by doing it as is, because 1 plus I divided by square root of 2 is still not a hard number. It's not the worst complex number. It's probably one of the easy ones to mess with for this type of thing when doing a lot of multiplying together. So 1 plus I divided by square root of 2 times 1 plus I square root of 2, and we have to multiply by itself until we get 1. Because then you'll have, because it's like, this is squared, it times itself. And when you cube it, it'll be this times the original, because that's square. Because 1 plus I squared divided by square root of 2 cubed is equal to 1 plus I squared divided by square root of 2 squared times 1 plus I divided by square root of 2, because that's raised to 1 power, and you add them. You add powers, so it'll be cubed then. And that's the idea behind this. As you can read over this to see what I've done. Listen to all these elements. There's 8 of them in the end, so it takes a long while. And there's no easy solution with this, because changing the polar coordinates is not really much. You're less likely to make a mistake if you really know how to convert, understand how to apply it, but it still takes just as much paper. It takes more work to some extent, even if it seemed like this a mess. In general, that's what you're supposed to do with complex numbers. If you can, just convert them. When you're raising them to powers like this, convert from the a plus bi form to the polar form. But first, I did it this way, and it works out. They match, so you should. But that's all you do, is all these operations, simplifying them down to a form that resembles what's going on above here. And you fill in this as you do each one. And at the end, I got 1, and then I do to the 9th power, and you can tell it's going to be 1 times it, so you'll get a repetition, 1 plus I divided by square root of 2. And so we don't include that. You generally, you basically won't ever do that. You don't even have to show that really, but it's just something I thought to show real quick. You can end at 1 though, because 1 times itself will be itself, and now I'll break the cycle. It'll end it. It'll show that it's already ended. What is the order of alpha? This is equal to number of elements in alpha, so order of alpha equals A. Cyclic group of alpha. As you can tell, you have 1, 2, 3, 4, 5, 6, 7, 8. So 3. Does beta to the 8th equal 1 for every beta in alpha? In general, this will be true because it's raised to the order. But you should still show it to some extent. But there is a way you can, think showing it also works. And I use some tricks like negative 1 plus I to the 8th would be negative 1 plus I to the squared to the 4th. So negative 2I to the 4th. Eventually you get 4I squared to the squared. Then 16I 4th divided by 16 eventually, because you're doing them all. And you get 1. All these work. Polar coordinates could also be used for this case. But it's quite obvious what happens. They're all going to equal 1 though. 1 raised to the 8th power. And now list all generators of alpha, of the cyclic group alpha. So, generator of alpha, the first, this is obvious. Obvious one is what it starts, the first element. I will not work. It only has 4. You need the 8 terms like before. And they have to be all part of alpha pretty much. So I is not a generator. And similarly, -1 won't be either. And -I won't. And eventually 1 won't. So there's 3 that we really have to test out the most. Ones that are not so obvious, ones we have to pay attention to. -1 minus I divided square root of 2. Kind of do this in my head for this, I didn't show it, but I think it'll be easier with polar coordinates too. But idea, and it does work out. Those are all each element. Even if they appear in a different order, it doesn't matter. So it's a generator. This is a generator. Basically, there's 4 generators. It's the first, the third, the fifth, and the 7th. All these terms that are actual complex number like format. 1 plus I divided by square root 2, -1 plus I divided by square root 2, -1 minus I divided by square root 2, and 1 minus I divided by square root 2 are all generators. Generators of the cyclic group alpha. And you can see here as well, that one works like I said, -1 plus I divided by square root 2. But what's more important is here. So let's say we start with alpha equals 1 plus I divided by square root 2. That can be written as 1 divided by square root 2 plus 1 divided by square root 2I. And that's A plus BI format. Rectangular coordinates. So with rectangular coordinates, we now convert this to polar. The modulus is 1, and it's going to be for each of these. If we convert any of these ones that need converting, they'll easily equal 1. Because it's all that 1 divided by square root 2 and 1 divided by square root 2. Basically, you square them, you get 1 over 2 plus 1 over 2, and then it's 2 over 2, so it's square root of 1 basically in the end. And that's 1. So you have positive cosine and sine are 1 over square root 2 and 1 over square root 2 because you're dividing A and B by 1, and they're both, yeah. And R, it's the R, which is, so with this all in mind, it's the first quadrant. You have T equals pi force. So that's what the inverse sine of 1 over square root 2 gives you in that quadrant. So Z equals 1 times this whole thing, so you can just say Z equals cosine pi force plus I sine pi force. That's what alpha can be written as. Original term alpha. And then, so this would be problem 1, just so you know, like you do this before then you can raise it to powers. And write it down like the same thing as before, you'll get all these answers. Alpha squared cosine 2 pi force, because it's even easier for this one because 1 is not in there. Because it's 1 times it, so 1 squared, 1 cubed, everything will always be 1 anyway, so you don't have to worry about it at all. It's really, and it's like that. You do get cosine of pi halves plus I sine pi halves, for example, for the second one, and that's cosine of pi halves is 0, and I times sine pi halves, sine of pi halves is 1, so it's just I, which even fits what we get in the first one, but you can see I. The -1 plus I divided by square root 2 you'll get in when you cube it, because it's cosine is 3 pi force. You're multiplying by 3 pi force. Cosine of 3 pi force will be -1, and sine of 3 pi force will be, no, it's not -1. I'm thinking of later. On the 3 pi force is negative. It's in the second quadrant, and sign will be positive. It's 1 over square root 2 and negative 1 over square root 2. And you can you divide out 1 over square root 2 to get them so that, you add up the like things. So it's negative 1 plus I divided by square root 2. I have it in the format as before at least. And you keep this up, you get negative 1, then you get more. You just keep on multiplying in that power into the angle. And now you use it for the other two parts, like 16.3, beta 8's equal 1 for every beta and alpha. You just convert these to polar coordinates and take them to the 8's power just. And you can read on in this, but this is like the other way of this is the way to do it, where you're less likely to make errors, I think, if you do the conversion right. The point after that, raising them to powers is pretty quick. And I think in general this is better in general because it ain't always going to be like that, but I think on a test you wouldn't have to go the extra mile with this anyway. Like it's a little bit harsh doing a cyclic group like this with complex numbers to some extent, because it takes a long time no matter what. But yeah, basically this is part 3, just getting polar forms of each and raise them to the 8's power, as you can tell. And see it equals 1. Each module is going to be 1. I label them Z2, Z3, Z4, and R2, 3, 4. Get them all. And we're going to use these in part 4, the last part when we do it. We really quickly look at that. These polar forms. So list all generators of it like before. I'm just going to focus on these really and I have the polar coordinate form of what matters. We're just going to do one of these really. It still takes a while. Negative 1 plus I square root 2 squared will be, I'll just say alpha 3, and alpha 3 is what this will be, negative 1 plus 1 divided by square root 2. You get the same thing as before. So it is a generator this way. But yeah, it works out as you can read on it. And you can try more on your own of this. You'll get the same results as before. I just did this one, and you can see it still takes. It's going to have other two, but I think that can be left to viewer. It's easier if you understand well using polar coordinates for complex numbers, basically. Which you kind of do need to know, so it's good. Like in the previous section. You have a good feel for it overall. You get the same numbers as when I first did these 4 parts. You get the same results. So yeah.